He just told me that they looked on the E-class at their marks, and that the mark that they actually got was different, presumably higher than the mark that's actually written down on the computer table. So you must all check the latest mark that's on the E-class and make sure that it corresponds to the percentage that you got. And if it doesn't, come and see me after the next lecture and bring your exam paper with you, because that's the last time that you'll have a chance to correct any errors that have been put in by the people who deal with this. I don't deal with these things. Okay, having done that, let me just remind you that in the last lecture I started to talk about substances called amines. They all have nitrogen, trivalent nitrogen, and I told you some of their properties, and I also described to you how an optically pure amine can be used to resolve a racemic organic acid. I went through the mechanism of that, and I showed you that if you take a racemic organic acid and you form a salt with a single enantiomer of an amine, you will get two salts. And the salts are actually diastereoisomers. And because they're diastereoisomers, they will have different properties. And the property we're interested in is the fact that they have different solubilities. So if you have two diastereoisomeric salts, one of them might crystallize very nicely from some solvent, and you can filter it off. And once you've isolated that diastereoisomerically, that particular diastereoisomer of the salts, you can then separate the salt into its components. Now, some of you probably regard all that as a bit strange, because all diastereoisomers that you've come across before are a single molecule. And when you're dealing with diastereoisomeric salts, it's really each salt is two molecules, but they're stuck together by electrostatic forces. But the entity is still diastereoisomeric. So if you've got an R acid with an R amine and an S acid with an R amine, this salt, I'll call it salt number 1, and that salt, which I'll call salt number 2, are diastereoisomers, even though there is no covalent bond between the acid and the amine, either here or here. So it's not actually strange, it's just that this is the first time you've come across diastereoisomers where each diastereoisomer is made of two components that are not joined together by a covalent bond. Well, having reminded you of that, let me now talk about the preparation of amines. And one of the ways of preparing amines is by using what is called the Gabriel synthesis. Now, the Gabriel synthesis gets around a problem that you will meet if you try to make an amine in what I suspect is the most obvious way. Now, the most obvious way of making an amine would be to take some alkyl halide and treat it with ammonia. And if you do that, you might well expect, and in fact you do observe, a nucleophilic displacement. And so you get this. But unfortunately, this stuff reacts again with the alkyl iodide. And so you now get that. And this also reacts with the alkyl iodide. And so now you get this. And that also reacts with the alkyl iodide, and the net result is that you get a complex mixture. So what I'm telling you is that the alkylation of ammonia or amines is generally not a good way of making another amine, because the product also undergoes alkylation. And so, in order to overcome this, Gabriel devised a method that avoids that problem. And the method is this. What you do is you take that compound, which has got a name, it's called phthalimide. And you can see that phthalimide has this unit here that I'm sort of circling with the tip of the pointer, and that's an amide group, and it's got another one over here. And when you have a nitrogen flanked by two carbonyls, here's one, here's the other one, that isn't called an amide anymore, it's called an imide. And so that's why this is phthalimide. And what you do is you deprotonate the nitrogen. You treat that with potassium hydroxide, and I will rub out all this alkylation attempt of ammonia. You deprotonate the nitrogen. And this is now something called potassium phthalimide. And that potassium phthalimide is a good nucleophile. And so if I take, let's see what amine we used a generic amine, so let's do that as well. The generic halide. Let's take an alkyl halide. It carries out a nucleophilic attack. An SN2 reaction to give you now an alkyl group on the nitrogen. Now remember that a few minutes ago I said if you try and alkylate an amine, the product gets alkylated as well, the product from that gets alkylated, and the product from that even gets alkylated, and so on. But in this Gabriel synthesis, once the first alkylation has occurred, this nitrogen is no longer nucleophilic. Why? Because it can delocalize, the lone pair can delocalize into the top carbonyl and into the bottom carbonyl. So the nitrogen on that first product is not nucleophilic. And therefore that product does not attack another molecule of the alkyl iodide or the alkyl bromide or whatever alkylating agent you're going to use. So the reaction stops here. So what we've done now is we've added one alkyl group to the nitrogen that's present in potassium phthalimide. And if we can somehow remove this part of it to release an NH2, we will have made a primary amine. With an R group, whatever we wanted. If we wanted ethyl, cyclohexyl, cyclopropyl, this, that, and the other, we would have made that compound. So the next step of the Gabriel synthesis is to disengage this part. And the way that that is done is to treat the compound with hydrazine. And if you treat this compound with hydrazine, what happens, I'm going to erase these little arrows that describe the resonance. What happens is that the electrons move on to oxygen. So let me write that down. And then the electrons move back and expel that nitrogen. Finally, oops, I made a mistake here. Sorry. Now, I've not shown all the proton transfers and various negative species picking up a proton. That's, we've got beyond that stage now. All that you need to know is that one of the nitrogens attacks the carbonyl, the electrons move on to the oxygen, then the electrons move back, expel this nitrogen, which picks up the proton, and then the other nitrogen of the hydrazine comes along and attacks the carbonyl, and then the electrons move on the oxygen, expels this, which picks up the proton. And now you release the primary amine. If you had tried to take ammonia and treat it with this alkyl iodide, you would have got this for sure, but this would have reacted again with the alkyl iodide to give you a secondary amine, and that would have reacted again with the alkyl iodide, give you a tertiary amine, and finally that would have reacted with the alkyl iodide to give you an ammonium salt. And I'll deal with ammonium salt soon. But by blocking two of the valencies of nitrogen with this dicarbonyl compound, you avoid all of that because this nitrogen, once you've deprotonated it, can attack only one molecule of the alkylating agent. And then the nitrogen is not nucleophilic enough to do anything further. And so you then remove this by bringing in a strong nucleophile that can attack this carbon, expel the nitrogen, attack this carbon and expel the remaining bond to nitrogen, and in that way liberate the primary amine. Now I'd like to show you an example of how to use this procedure to make a complicated primary amine. Supposing I wanted to make this particular primary amine, there are various ways I can make an amine, but supposing I wanted to use the Gabriel synthesis. If I want to use the Gabriel synthesis, I know that that nitrogen must come from potassium shalimite, and the rest of the carbon chain comes from some alkylating agent, which might be an iodide or a bromide or something like that. And so what I would do is to take phthalimide and treat it first of all with potassium hydroxide to make the salt, and then treat it with a suitable alkylating agent. And if I do that in exactly the same way that I drew on the board 3 or 4 minutes ago, I would get that compound, and finally, if I treat that with hydrazine, oops, we don't want to do that. I would liberate the amine that I want, and the other component, and they're totally different compound classes, which therefore I can separate them very, very easily. So that's an example of using the Gabriel synthesis to make an amine, and all you need to realize when you see an amine and you want to use the Gabriel synthesis, all you need to realize is that nitrogen comes from potassium phthalimide. And the other part of the amine, whatever carbon unit is stuck onto the nitrogen of the primary amine, that comes from an alkylating agent, which could be an iodide or a bromide, maybe even a chloride, and certainly a tosylate. Now, I mentioned a little while ago that if you try to alkylate ammonia, the nitrogen will displace the leaving group to give you a primary amine. Then that nitrogen of the primary amine attacks the alkylating agent again, you get a secondary amine, and so on. And right at the end, I said you then get an ammonium salt. So let me just draw more clearly for you the business of forming a salt. If you have some amine, let's just take trimethylamine, and you treat it with methyl iodide, you will get a quaternary ammonium salt, as it's called. It's just an SN2 reaction. There's a plus on the nitrogen, and then you have a negatively charged leaving group. Now the amines there's one other method for making, one other nice method for making alkyl amines, and that involves taking an alkyl halide, let's say an iodide, and treating it with sodium azide, and what happens is you get an SN2 reaction. You end up with an azide, and then you reduce it. Either hydrogen and a catalyst, or lithium aluminum hydride. And what happens then is that you get the amine. So that's another way of avoiding the problems that you meet if you try and simply alkylate ammonia or a primary amine. So you make an azide, and you then reduce the azide group to release the amine. Now, all the compounds, all the amines that I've mentioned so far, have had the nitrogen on an alkyl group, methyl, ethyl, propyl, cyclohexyl, and so on. What about nitrogen on a benzene ring? How does one make that type of compound? Well, the way one makes that, a very good way of making that, is to go from a nitro compound and reduce it. If you reduce a nitro group, you get the corresponding aniline. And the way that you can reduce it is hydrogen and a catalyst, or you can use iron and hydrochloric acid. And so if you have supposing you want that compound, and what you have in the storeroom is that compound, what you would likely do is to do an electrophilic aromatic substitution, electrophilic aromatic substitution, and you would get as one of the products the nitro compound, and then you could reduce it by heating it with iron powder and hydrochloric acid. So this method of reducing a nitro group is a very, very useful method of making anilines. And anilines are simply substances that have an NH2 on a benzene ring, or in general, trivalent nitrogen on a benzene ring. So NH2, NHR, NRR prime. So it's an amino group on a benzene ring. One of the ways of making it is by reduction of a nitro group. There's yet another way of making amines that's called reductive amination.
Too bad we already did this.
Yeah,
I know. Actually.
I'm actually kind of sad this is not on our lab exam, because I actually kind of understood this one
Yeah.
more than like the other ones, right?
Yeah.
But no, it's not going to be tested, just the other harder ones.
Maybe it's because it's like the most recent one.
Yeah, and because we don't get our it back.
And finally, they're all very similar. I will explain them in a moment. So what's going on here? What's going on is we start with a carbonyl compound, and we add some nitrogen, some amine, either ammonia, or a primary amine, or a secondary amine. Doesn't work for tertiary amine, so it only works for ammonia, primary amine, secondary amine. That's the first step, but in the second step, this H in brackets means we reduce it. So one of the ways of reducing it would be to have hydrogen and a catalyst like palladium charcoal. So if you take a ketone and ammonia and hydrogen and palladium on charcoal, you will get this. And if you do the same sort of thing with this, again, you'll get the indicated product. And likewise, if you do the same sort of thing with the secondary amine, you'll get this product. Now, instead of using hydrogen and palladium charcoal, there are some hydride reducing agents one can use, and sodium, cyan, so let's write that down, sodium, cyano, hydride in acid. Now, what's going on here? There's obviously something fairly complicated going on. And what happens in all these cases is, let's do it for a primary amine. What happens is you get an imine, and I've mentioned the formation of imines before, it's acid catalyzed, and then the imine is reduced, either by hydride or by hydrogen. Now that reduction, if you're doing it with hydrogen and a catalyst, might look a bit strange to you, but I'll explain why it shouldn't be strange, because you all know that a carbon-carbon double bond, if you have a compound with a carbon-carbon double bond, you shake it with hydrogen and a catalyst like palladium on charcoal, the ends of the double bond pick up hydrogen and the double bond disappears. Well, all we're doing here is to take a double bond, it's not between two carbons, but it is a double bond, and we're adding a hydrogen at one end and a hydrogen at the other end. If you do that, you get an amine. If we use sodium cyanoborahydride, this is a source of hydride ion. So a hydride ion will come in here, the electrons will move onto there, and that will pick up a proton. So there's nothing terribly strange about this reduction of a carbon-nitrogen double bond. It's just the nitrogen animal of reducing a carbon-carbon double bond, except for one difference. In the case of a carbon-carbon double bond, you can use hydrogen catalyst. Likewise, for a carbon-nitrogen double bond, you can use hydrogen catalyst. But it's only for the carbon-nitrogen double bond that you can use a so-called hydride reducing agent like that. The reason is that all those reagents attack a carbon that's polarized. And you need a carbon that is not a doubly bonded carbon that isn't joined to another doubly bonded carbon. It has to be joined to oxygen. You can use a hydride reducing agent to reduce aldehydes or ketones. So you need a heteroatom, and in this case it's nitrogen. So that's one of the ways of that's another of the ways of making amines by so-called reductive amination. Now, to make sure you understand this, I ought to show you a few specific examples.
He's about a week late.
Oh, goodness, yeah. Oh well, maybe it'll help with the lab.
That's true.
You need to go over like everything.
Yeah.
I have a meeting every day this week.
Really? Out of nowhere. Wow.
If only we were a cartoon.
Supposing I wanted to make that
That'd be pretty funny.
using reductive amination. I could, of course, make it using the Gabriel synthesis, in which the nitrogen would come from potassium phthalimide. Then I'd have to use an alkylating agent, which would be benzyl bromide. But supposing I want to use reductive amination, that means I need an amine and I need a carbonyl compound. Well, if you work backwards, the carbonyl compound that's appropriate is benzaldehyde, and the amine that's appropriate is ammonia, and one of the ways of doing that is hydrogen and nickel over nickel. Supposing, however, that this is my target. And I want to make that by reductive amination. You see, that is a secondary amine. This one's a secondary amine, so I can't use the Gabriel synthesis because the Gabriel synthesis gives you primary amines. If I wanted to make this by reductive amination, then the reduction of the nitrogen to carbon double bond could be here or here, depending on which amine I have. Let's make it from benzaldehyde again. And if I make it from benzaldehyde, what I need is that amine, and then perhaps I would use sodium, cyano, or a hydride. And finally, supposing I wanted this amine. This is a tertiary amine, and so again I can't make it via the Gabriel synthesis because that gives only primary amines. But I can make it by reductive amination because if I treat that with dimethylamine with an acid catalyst, I will get, as an intermediate, that salt, and then I can reduce that with sodium, cyano, or a hydride. Okay, supposing I'm given this problem. I have to make this quite complicated amine, and that my starting material is benzyl bromide. So I've got to work out how to assemble this compound A, and I can use as one of the organic starting materials benzyl bromide. Now, if you look at benzyl bromide and you look at this structure, obviously the benzene ring and that carbon must come from the benzyl bromide. So just by looking at the nature of the problem, I know a little bit about where at least part of this structure will come from. But how do I get these extra carbons? What I really want is I want to introduce more carbons, because what I would really like is to make this by, well, there are several ways, but supposing I want to make this by reductive amination. If I want to make this by reductive amination, you can tell that what I really need is a ketone. And then I will treat the ketone with ammonia and a reducing agent. So this thing, if I'm going to use reductive amination, will come from that ketone. So I need to be able to make that ketone from benzyl bromide. Now, if I look back over my notes for this course, I can see that one way of making a ketone would be from a Grignard reagent and a nitrile. Because if you add a Grignard reagent to a nitrile and then hydrolyze mixed, you get a ketone. Now, since I know that benzyl bromide is my organic starting material, it now becomes clear that what I have to do is an SN2 displacement on the benzyl bromide. So that gives me the nitrile, and the nitrile can then be converted into the ketone, and the ketone can then be subjected to reductive amination, which would be ammonia and hydrogen and a catalyst. So what I've done in the last few minutes, I've taken a rather complicated example. I'm not pretending that it's easy. And I've shown you one of the ways. There are numerous ways of making that compound. There are several ways of making it from benzyl bromide. I've shown you one of the ways of making it using reductive amination. Now, you can see from this that there's no hard and fast set of rules that tell you this is how you work out how to synthesize a compound, or this is how you work out how to synthesize an amine. It's a much more complicated business than just following a set of rules. But one of the usually very fruitful ways of tackling a problem like that is to look at the final product and ask yourself, can I recognize any pieces in it that I got in the storeroom? Well, here you're told benzyl bromide, so you know where the benzene ring comes from. And then you look at the product and you say, well, this product is a member of such and such a compound class. In this case, the compound class is primary amine. Do I know any ways of making primary amine? And if you know 2 or 3, you just write them down. And the one that I talked about most recently is reductive amination. So you say to yourself, well, I wonder if it could be made by reductive amination. If it is going to be made by reductive amination, it'll have to come from a ketone. Is there any way in which I can take benzyl bromide and convert it into the ketone that I obviously need? Then there's a bit of a gap because in your logic, because you've then got to say, well, how do I make that ketone? Well, what ways do I know of making ketone? You probably know a few ways, and for each of those, you've got to write them down, and then you say, well, if I'm going to use this way, what will I need? And then you go on to the next method. If I'm going to use that way, what will I need? So it's like a tree, it branches out, and you can understand that the number of branches increases enormously, very, very quickly. So it isn't an easy business in working out how to make compounds. But here is a way that you should be able to handle based on the things that I've told you. Now, what you should do to make sure you can handle these things is to do homework problem 20.5, which is also 20.5 in the 9th edition.
like an hour and a half.
Oh yeah.
Yeah.
Yesterday was so boring. I wanted to die.
No one showed up, or 3 people showed
No,
up.
we actually had more than you guys.
Oh, okay, that's good. I actually thought it would be really, like, a lot of people.
I expected us to be in like a gymnasium.
Yeah, like a booth kind of thing, right? So, hey, Tara, I've never been to them either. Someone took us there, and she was like, this is what they recommended. Because they told her to do that.
Oh,
She wasn't. She didn't even know what it looked like.
If you reduce any of these compounds either a nitrile or an oxime or an amide, it can be a primary amide, secondary amide, or a tertiary amide. If you reduce any of these compounds, you will get an amine. In the case of a nitrile, you get a primary amine. In the case of an oxime from an aldehyde, you get a primary amine. In the case of an oxime from a ketone, you also get a primary amine. And for an amide, you get an amine which could be primary or secondary, depending on what type of amide you have. And you should do question 20.6, which is equal to 20.7 in the 9th edition. Now, I'm sure some of you are getting a little bit concerned that there seem to be quite a lot of ways of making amines. And there's nothing I can do about it. There are quite a lot of ways of making amines. And I need to tell you another one that's rather complicated. But don't worry, I will explain it, make it very, very clear. For a variety of reasons. One is, it was developed by Professor August Wilhelm von Hofmann, who was the first professor of organic chemistry at my university. He was 24 years old, and he became professor of chemistry at Imperial College. And the way that he became professor of chemistry at Imperial College is that the husband of Queen Victoria decided that England ought to have a super duper science university, and he wanted to get the very best in all the departments, and certainly in chemistry. So he asked the most famous German chemist, a man called Bayer, if he'd come and be professor there. It's in a very nice part of London, South Kensington, near a beautiful large park, very, very expensive area, very nice. And this professor said, no, but I got a pretty smart student and he'll do the job very well, which in fact he did. So I want to tell you about the Hoffmann rearrangement, named after August Wilhelm von Hofmann. Okay, if you take a primary amide,
Oh, there's only one F.
There's two. There's always two.
There's two M's. I got that there.
If you take a primary amide and you treat it with bromine and sodium hydroxide, you get a primary amine. So you can see what's going on. What's going on is this R group somehow becomes attached to the nitrogen and this carbon disappears. So clearly there's a very extensive reorganization of the atoms, and one of them is removed. Now what is going on? Well, if you take the amide and you deprotonate it with sodium hydroxide, and you treat that with bromine, that's the first thing that will happen. You get an N-bromoamide. Now, it's not 100% clear exactly what happens next. There are several possibilities, but I will show you one of them because it's easier to understand. That's quite a lot to follow, but once you've copied it down, I will talk you through it and show you that it's all very logical. And I'll probably have to do it again in the next lecture. So, in the last minute, we have an amide, it's got acidic hydrogens, there's no problem about understanding how you could remove one of those hydrogens by treating it with a base. This now becomes nucleophilic, attacks bromine, so you get now an N-bromoamide. Now this N-bromoamide still has an acidic hydrogen, so the base can remove it, put the negative charge on nitrogen. Now, if the bromine then departs with a pair of electrons, it will come out as bromide. But the nitrogen, which started off negatively charged, will now be neutral. And the neutral nitrogen joined by one bond to something else is called a nitrene. Now, if this pair of electrons here moves onto the nitrogen, and at the same time a pair of electrons on the nitrogen moves into that region, the nitrogen gains the share of the pair of electrons, but it loses control over this pair of electrons that have moved there. So the nitrogen, which is neutral here, stays neutral here, except now the bonding is double-double. Now if water or acid or the base comes in here, it can pick up hydrogen on the nitrogen, and now you have an N-carboxyamine. An N-carboxyamine leaves CO2 to put a proton on the nitrogen. In other words, you get CO2 coming out, you get a primary angle. I'll go over that again next time. Thank you.